Hey students, in this video we're going to be discussing lines and curves in space. You will need to use GeoGebra, so make sure you have it available. All right, so let's get through this wall of text. All right, so vector value functions are just vectors that have equations for each of the components. In component form, we would have just the three functions separated by commas inside of some pointy brackets. In terms of the unit vectors, remember in R3, our unit vectors are I equals 1, 0, 0, J equals 0, 1, 0, and K equals 0, 0, 1. So just the two ways we'll see vectors written for the rest of the course is either in component form or in terms of the unit vector. They mean the same thing. All right, so the first thing that we're going to cover is how to write a line, the equation of a line given 2 points or given a point and the direction of the direction vector. So we already know to write a vector to get the component or the direction, we take the ending point, and from it, we subtract the coordinates of the first point. So that's how we arrive at this formula: x2 minus x1, y2 minus y1, z2 minus z1. Note PQ and QP are not the same vector. They move in opposite directions. So we can parameterize the line equation for our vector by using this formula x1, y1, z1 plus ABC times some arbitrary value t. And ABC is the direction of the vector. That's the x2 minus x1, y2 minus y1, z2 minus z1. And we're going to parameterize that so that we can express the equation of the line as a projection into some plane, because that tells us more about how the graph behaves. Generally for us, z is going to be the component that adds depth above or below the xy plane, but a projection onto the xy plane is going to tell us how the graph behaves. So we'll need to be able to solve for the equation of the line in terms of x and y, or y and z, or x and z, or something. So for our first example, we want to find the equation of the line that contains the point 2, 0, 1, and it moves in the direction vector 3, 1, 2. So let's make an equation where we have r of t equals, so now our formula is x1, y1, z1 plus our direction vector a, b, c. We'll need a third comma. A, B, C, T. So for us, R of T is going to equal, so X1 is 2, Y1 is 0, X1 is 1. And we're going to add 3, 1, 2, T. So now in terms of components, X is going to equal 2 plus 3T. Y is going to equal just 0. We'll say 0 plus 1T, but that's really just T. And then our Z component is going to be 1 plus 2T. So these are the two ways that we can write the equation of the line. 1 is in its vector form, and 2 is parameterized for each component. Let's do something extra where we project the line onto the XY plane. We're going to do this in the next example, but I want you to pause it and see if you can do it and come back and see if you get what I get. So let's see how we actually do that. So if we project this onto the XY plane, the implication is that the Z coordinate is 0. So we don't care about it. So if Z is 0, then what we want to do is solve for T in one equation and replace in the opposite. And solve for y. So what we have is x is 2 plus 3t, and we also have y is 0 plus t, so y equals t. So now conveniently, that works out nicely, because then we can just do a direct replacement. If y equals t, then x is equal to 2 plus 3y, and so then x minus 2 divided by 3 equals y. And if you like your equations in, I don't know, slope-intercept form, you tell me something like y equals 1/3 x minus 2/3. Cool. So this is the projection of that line onto the xy plane. We'll see more about this when we do stuff in class with GeoGebra. So in this one, you pause the video, see if you can come up with the equation of the line, and then project the line onto the xy plane. All right, so if you're joining me, first we need to find our direction vector. So our direction vector is 2 minus 1, 4 minus 1, and 3 minus 1. So that's going to be 1, 3, 2 as a direction vector. And so since we are going from W0 to W1, that means that our equation needs to have W1 as the first point. So that's going to be 1, 1, 1 plus our direction vector. So that's going to be 1, 3, 2 times t. And so we're going to get x equals 1 plus t, y equals 1 plus 3t, and z equals 1 plus 2t. Cool. So if we want to project this onto the xy plane, we're going to do the same thing. We don't care about the z. What we want to do is solve for t using either the x or the y equation, x or y parameter. So since x equals 1 minus t, that's going to tell us that x minus 1 is equal to t. I may have said x equals 1 minus t. I meant to say x equals 1 plus t. So x minus 1 equals t. So if x minus 1 equals t, we can substitute that here. So we get y equals 1 plus 3 times x. Whoa. Y equals 1 plus 3 times x minus 1, which is the same as 3x, minus 2. Cool. So the projection of the line onto the xy plane has the same, it behaves, other than being above or below the xy plane, is going to behave like the line y equals 3x minus 2, this directed line. Cool. So that's how we make the equations of lines using a couple of points. So next, we have the domains of vector value functions. And this is going to be what you think it is. It's the values of t that we can get a point for. When we have three components, we have to consider the parameters of the domain of the individual components. And where they all overlap is going to be the domain. So for this, we know for the square root of t, the implication is t has to be greater than or equal to 0, or that's the same as t is in the interval 0 to infinity. For t squared, t can be any real number, and the same thing for sine t. T can be any real number. So you always take the strictest requirement when you're looking for the domain. So in this case, the domain is what makes that first component work, the x component. So our domain is t is in the interval of 0 to infinity. All right. For the next one, we have, you pause the video, see if you can get it. So if you're rejoining me, our first component, we need to be concerned with 9 minus t squared. Now, you should know that this is a semicircle of radius 3, so it's only going to be defined for values between -3 and +3. But I'll let you work that part out. So in this case, so t is an element of the interval -3 to +3. But because we're taking a square root, we actually don't need the brackets. We actually need parentheses. So t is strictly some value between -3 and +3 for the first component. For the second component, I should have put that square root. For the second component, we have the square root of t plus 1. And in this case, we're going to need t to be greater than, so that's going to tell us that t is greater than or equal to, well, greater than or equal to -1. So in this case, t is an element of the interval -1 to infinity. And for our last one, we have the component 1 over t minus 1, which is going to imply that t just can't be 1, which is the same as saying t is anything from -infinity to 1 union 1 to infinity. So when we consider all three of these things, so far, this is the strictest component. We have to start at least at -1, but then for the second component, we can't exceed 3. I'm sorry, for the first component, we can't exceed 3. And for the third component, t can't be 1. So in total, our domain is t is an element of the interval -1 to 1 union 1 to 3. Those are the values that will work for all three components at the same time. Nothing else outside of those things would work. So again, the reason we don't go to infinity is because the first component can't go to infinity. So that's going to impose that we start at 3. And the reason we don't begin our domain at -3 is because the second component has to start at -1. And the reason we exclude the 1 is because the third component t can't actually be 1. So lastly, we're going to plot a function. Oh, not lastly, last for like the curve stuff. So we're going to plot this function in GeoGebra. Do I have GeoGebra open? I do. So I think the components were square root 9 minus t squared. So to plot this, we need to just put in 3 components. So we have the square root of 9 minus, can I get the whole alphabet? How do I do that? Oh, ABC. 9 minus t, and we want that to be squared. And then the second component was t, and the last component was, all right, actually, let's stop here for a moment. So the first thing that we do to understand how the curve behaves, you want to project it onto the xy plane first. So we see this as a semicircle of radius 3. And generally, we're going to want time to be positive. So instead of making this start at -10, let's make this start at 0. And now, so if we orient this the right direction, so we can see that when t is 0, our x is going to start at 3 and our y is going to start at 0. So how can I tilt this? All right, here we go, like this. So when t is 0, our x is 3 and our y is 0, and so forth. And you know what? Actually, let's put a point on here. Let's call, we're going to say a point B. Where's the equal? So B is going to equal, and we're going to make B equal A of, no, actually, we need a slider for B. I'm sorry. So we're just going to, give me just a moment. So we're going to make a slider for B, and we're going to go to settings, and we're going to make that minimum value 0, the maximum value 3, and we're going to make an increment by 0.1. Cool. And so then we want this point, we'll say, I don't know, C equals A of B. Why is that not giving me that point? Just a moment. Oh, yeah, it should. Oh, yeah, it's actually working out now. So now if we trace this, it's giving us a vector now. So we sweep this around. So we can see that when we start at 0, we're here. And as we move, we're going to end up on the y-axis. So now in 3 dimensions, what the curve looks like is we just need to add that third component. So hold on a moment. So we had square root of 9 minus t squared. The other one was t. And I think the third component was sine t. Sine. We should just be able to put in t. Yeah, sine t. And so we're going to make another point. We'll say capital P. So P is equal to the point, and we want it to be based on that curve. So our curve is A, so we're going to say P is A. Nope, D actually. You want to use that D curve. So D of B. D of B. And we can add a slight, so if we change, so if you look at the projection of the curve, so when we start at 0, actually, let's make this go to negative. So we can actually see what's happening. Negative, we'll start at -3. Cool. So when we start at -3, the curve itself is actually below the XY plane. So remember, the Z is only going to add like a up or down direction from the XY plane. It's going to give us some depth. So when we trace this point along, the point is moving from below the XY plane to above, but the X and Y are moving according to this semicircle. So it kind of looks like a roller coaster, but this is how we can use GeoGebra to understand what the curve is actually doing. So again, if T had to be positive, we start here and just move forward. So it's going to go up, hit a maximum, which we'll talk about when we get to more calculus, and just go back down to 0. So that's how we use GeoGebra to understand some points. All right, so limits and continuity. So just like we did in single variable calculus, the limit, if you can substitute in the limit value, substitute in the value, and whatever you get, that's the limit. And we'll talk about continuity in class, but the same rule for continuity that exists in single variable calculus, the limit has to equal the function value. That's also going to be true for vector value functions. It's just trickier because we can approach in a lot of different directions. So we'll see lots of examples of what happens when the limit doesn't exist in class. So for A, the limit as t approaches infinity, the limit as t approaches pi is just going to be, so pi doesn't give us any problems for the first component. You can substitute in pi for the second component and for the third without getting a negative square root or dividing by 0. So we're going to get the cosine of pi over 3. It's going to approach this. So cosine pi over 3, and then pi divided by pi minus pi over 2, and then the square root of pi squared plus 8 pi squared. So the cosine of pi over 3 is 1/2. Pi minus pi over pi divided by pi minus pi over 2 is pi divided by pi over 2, which is the same as pi times 2 over pi. So it's obviously a half. So we get a half. And then the square root of pi squared plus 8 pi squared is the square root of 9 pi squared. So that is just 3 pi. For B, so remember tangent is sine divided by cosine. And tangent, so cosine is 0 at pi over 2. So for our first component, we would get 0. For our second component, we get 1. For this third component, since it's sine over cosine, we would get undefined. So what this is going to imply is that the limit does not exist. All right, so that's limits. Substitute the value in if you can. All right, so that concludes this video on lines and curves. Sorry about that long thing in GeoGebra, but otherwise, pretty straightforward. For lines, we just subtract the 2 points to find our direction vector. For the domain, it is the combination of all of the different domains that work for all of the functions. And for plotting curves in GeoGebra, plotting into the XY plane helps us understand how the curve behaves. And then the Z adds the height above or below the XY plane.